Every day, students walk thousands of steps across the LSU campus. With each stride, their bodies are generating forward and rolling motion that normally goes unused. For this project, we were tasked with creating a device that could harvest wasted energy and convert it into something useful. Our goal was to design a system that works naturally during regular walking and produces reliable, measurable output. This video explains how we developed the solution using the engineering design process. To focus our work, we chose a client who represents the average LSU commuter student. This client walks long distances every day, carries a backpack, and needs a lightweight energy harvesting device that functions without changing their normal routine. Their needs became the foundation of our design requirements. After we identified who our client was, we then organized their needs into a structured set of engineering objectives. We created an objective tree to translate what the client wanted into measurable design requirements. Our purpose was to harvest and utilize wasted energy for mechanical movement. Everything else in our design stems from this core objective. The first major branch focuses on harvesting useful energy. This includes capturing mechanical motion, converting it efficiently, and ensuring the device is portable, lightweight, and easy to integrate into daily walking. The second branch emphasizes producing meaningful output. Our design needs to generate sufficient energy, provide reliable output, and do so consistently during normal walking. To objectively evaluate our concepts, we created a comparison chart using criteria from our objective tree. These criteria included the ability to harvest mechanical energy, ability to be built within the project timeline, independent operation, ergonomic design, meaningful energy capture, durability, safety, and cost. The objective tree also helped us avoid drifting away from the client's most important needs as the project grew more complex. It gave us a constant reference point, letting us check each decision against measurable design criteria. Having this structure early on ensured that our late concepts and prototypes aligned with both customer expectations and real engineering constraints. When we scored each concept, the backpack carrier consistently outperformed the alternatives. It scored positively in nearly every category, including safety, durability, and meaningful energy capture. It was also the most practical to build before the October deadline. Some of the other ideas included pneumatic shoes, a handheld energy harvester, a push scooter, and kinetic tiles. Pneumatic shoes and a handheld energy harvester had partial advantages, but came up with higher complexity or lower energy output. A push scooters and kinetic tiles performed the worst overall because they were either impractical for our users or required environments outside the user's daily routine. To support this process, we also created a decision matrix based directly on the objective tree. This allowed us to score each concept consistently and choose the idea that offered the best balance between feasibility, performance, and safety. The decision matrix didn't just help us pick a concept, it helped us understand why certain ideas failed. Concepts like kinetic tiles or scooters scored low not because they couldn't work, but because they didn't realistically match how our client moves through their daily routine. The matrix made these trade-offs clear and allowed us to confidently commit to the backpack-based rolling system. The total scores clearly showed that the backpack carrier was the strongest concept. This analysis led us to select it as our final design direction. After this, we began to start prototyping. Our first prototype focused on testing whether we could convert rolling motion into usable rotational energy. Version 1 used a single motor mounted on the side of a dolly, a rubber band wrapped around both the wheel and the small flywheel connected to the motor shaft. As the dolly rolled forward, the rubber band spun the flywheel and generated electricity. However, this early prototype had several limitations. The wheels did not yet have grooves, so the rubber band had frequently slipped or shifted during rolling, causing inconsistent rotation. The single motor produced very low output, and we had not yet incorporated any electronics. Several issues became immediately clear, including unstable rubber band alignment, inconsistent wheel contact, and the lack of any dedicated motor mounts, all of which reduced reliability and output. Without motor mounts, the motor was able to shift during rolling, creating vibration and misalignment that further reduced the effectiveness of the flywheel. Version 1 also taught us just how sensitive the system was to alignment. Even small shifts in the wheel, rubber band, or flywheel caused noticeable loss in rotation. This helped us understand that improving stability wasn't just a minor upgrade, it was essential for producing electrical output. These insights helped guide our direction for version 2. Version 1 confirmed the basic rolling to rotation concept work, but it also revealed the mechanical and electrical weakness we needed to address next. We also realized that our energy transferring system depended heavily on smooth, controlled motion. Any shifting, wobbling, or slipping in version 1 directly reduced the rotation of the flywheel. This made it clear that the stability and alignment were just as important as the motors themselves. In version 2, we improved the system by adding a second motor on the opposite side of the dolly. This allowed both wheels to harvest energy simultaneously, doubling the potential mechanical input. We also added grooves to the wheels so the rubber bands would sit securely and transmit rotation more reliably. Adding proper motor mounts in this version eliminated the shifting issues from version 1 and gave us a much more stable and consistent rotation. With these mechanical improvements, version 2 finally began to demonstrate that our energy harvesting approach was possible. The system now behaves predictably, which gave us the confidence to begin integrating real electronics and preparing for a full prototype build. For this version, we focused on durability, safety, and consistent output during real walking. Version 3 became our final integrated prototype. This version included fully assembled electronics, we improved wire routing, secured the motors and flywheels, and ensured the rubber bands operated smoothly during extended rolling tests. The final prototype includes dual motor harvesting, reliable rubber band connection, stable electrical output, and a design that could operate naturally during regular walking. Version 3 is still an open, breadboard-based prototype rather than a fully packaged product. The electronics are mounted externally on a breadboard, and none of the components are enclosed inside a dedicated housing. The structure itself is built on top of a modified dolly platform rather than a frame designed specifically for this system. Even though the prototype is mechanically and electrically functional, it has not yet been integrated into its standalone enclosure. Even though version 3 successfully combined all working elements, its open layout allowed us to see exactly where an enclosed design could improve performance, safety, and durability. This version gave us the blueprint for how a fully contained device would behave and what structural features we would need to add next. If we were to move to a version 4, our next steps would be to focus more on it being a standalone product rather than a bunch of pre-built parts put together. We would design our own custom frame instead of relying on a dolly, allowing us to optimize motor positioning, wheel spacing, and structural integrity. We would replace the breadboard with a compact PCB and add a full rectifier circuit so both motors could combine into a stable DC output suitable for storing and charging. We could also explore optimizing the flywheel size and mass. A larger or heavier flywheel could store more rotational energy, improving both the smoothness of power delivery and overall efficiency. Finally, we could move the electronics to be enclosed so all the electrical components would be fully encased inside a protective housing to improve safety, durability, and weather resistance. Version 3 proves that our concept works, and it provides a clear foundation for how the next iteration could evolve into a polished, enclosed, consumer-ready device. To help us with prototyping, we created a Fusion 360 model to visualize the internal layout and confirm the layout between components. The CAD model allowed us to analyze motor placement and wheel spacing before physically assembling anything. Here, we show our exploded assembly animation. In this view, each component is separated so the internal structure can be seen clearly. The wheels, dowel rods, flywheels, motor mounts, and rubber band path are all shown individually. This helped us verify that the belt drives would align properly and that both the motors would be positioned symmetrically to draw energy evenly from each wheel. This modeling process also showed how much unused space could be reclaimed in a future enclosure, and also how compact and efficient a purpose-built version 4 frame could actually be. We also modeled the framework used to secure the motors and flywheels. This step was important to ensure that both the motors remain rigid under load, preventing vibration and misalignment during rolling. The exploded view also provided an early visual reference for how a future enclosed version 4 would look once all the electronic and mechanical parts are fully packaged inside a single housing. Next, the animation recombines the assembly, showing how the system fits together in its final prototype form. The motion demonstrates the rolling action, and as the wheels rotate, it carries the rubber bands, which in turn spins the flywheels that are attached to the motor shafts. Making a model allowed us to confirm that the flywheels had enough space for rotation and that potential points of friction or interference were avoided. The CAD model didn't just help us visualize the assembly, it gave us a clear picture of how much space could be saved in future enclosed versions. By examining the layout digitally, we identified areas where supports could be strengthened, where components could be compacted, and how a complete housing could improve durability. This guided many of our expectations before we began performance testing. Using Fusion 360 throughout the design process helped us understand spacing, tolerances, and structural layout before manufacturing. It also gives us a clear visual of how the mechanism functions together as a single system and how a fully enclosed version 4 could be built around these internal components. To evaluate the performance of our final prototype, we conducted multiple walking trials. Each participant pushed the dolly for a distance of 20 meters at their natural walking speed while we recorded the time, calculated speed, and measured the battery voltage before and after each trial. Across all 6 trials, the device consistently increased the battery voltage by about 2 to 3/100ths of a volt. This might seem small, but for a system powered by only passive rolling motion and dual motors, it demonstrates that the mechanism reliability converts walking energy into measurable electrical output. The bar chart shows the change in voltage for each trial. 5 of the 6 trials produced a total of 0.03 volts, and 1 of the trials produced 0.02 volts. This consistency indicates that the system performs similarly across different users and walking styles. The line plot compares walking speed to voltage change. Although the speed varied slightly between users from about 1.25 to 1.4 meters per second, the voltage output remained nearly the same. This tells us that the energy harvested is primarily tied to the rolling of the system rather than the differences in the user's speed. Overall, the data shows that the prototype produces repeatable, measurable electrical output using only walking motion, confirming that our design meets the project requirements of harvesting energy passively during normal movement. Through this project, we applied engineering design process to convert natural walking motion into usable electrical energy. Starting from our client, a typical LSU student walks a long distance each day. We developed a clear objective, explored multiple concept ideas, compared their feasibility, and redefined the design throughout 3 different prototype versions. Our final prototype successfully demonstrates passive energy harvesting using rolling motion, and the dual motor systems, flywheels, and test circuitry work together generate consistent measurable voltage during normal walking. Our performance data shows repeatable output across multiple users, confirming that the system meets the core project requirement of harvesting energy without adding any extra effort to the user. Although version 3 is functionally complete, it remains an open prototype built on a dolly with a breadboard electronics. A future version 4 would integrate enclosed electronics, a custom designed frame, a dedicated rectifier circuit, and optimized flywheel sizing to further improve efficiency and durability. Overall, this project taught us the importance of integrative design, problem solving, and evaluating trade-offs between mechanical performance and electrical output. It also showed how even small amounts of everyday mechanical motion can be transformed into a meaningful amount of energy. Altogether, the design process highlighted both the potential and the challenges of harvesting energy from walking. It also helped us understand which improvements would make the system more efficient in future versions.